So are there any questions that you would like to go over from the homework, from in-class activities, from anything that maybe was confusing to you, any concepts you'd like to review?
You said you're going that you don't have to know interpolation. The reason why I'm asking is because I was reviewing homework problem number 1 and 3, and your interpolation in the solution for row 4 was completely different from the equation you gave us. And I couldn't get the correct answer.
For homework 4?
Chapter 3, homework number 1.
Okay.
I've tried 3 different times. I couldn't get your answer.
Oh, because this is not the equation, my equation for interpolation.
So we just stick with the one you gave us, correct?
Yes, but it's not going to be on the exam. You don't need to interpolate on the exam.
Okay.
Yeah, so there are a lot of different ways to do interpolation. As long as you're, for all the homeworks and stuff too, as long as you're close and you show me that you tried to interpolate, like it's fine. I'll correct this with my equation. Other questions? Oh, one of the things that I forgot to add, one of the things that's also fair game is boundary work and boundary work. Please bring your calculator and please bring a pencil and an eraser. You don't need to bring anything else. Okay, anybody like to go over anything?
Can we do some of the last problems from homework number 3?
Last problems from homework number 3. Yes. Anyone in particular? Like the FE style questions or?
No, not the FE ones, like the bigger paragraph ones.
Okay. Yes, we can. So the one with like the heating of a pipe.
Yeah, like 4 and 5, those would be good.
Okay. So I'll tell you number 5 is a good homework question and it is not a good exam question. So I think it might be better to go over homework 4. Homework 3 question 4, just out of like preparing you for the exam a little bit better. So I can definitely go over that one. I think the tricky part of this one is you don't often work with the area of a pipe. So I'm sure most of you probably had to Google like, what's the area of a pipe? On the exam, I would give you that. Okay, so for question 4 on homework 3, we are asked here, saturated steam coming off a turbine of a steam power plant at 40 degrees Celsius condenses on the outside of a pipe. So it changes from steam to saturated liquid. So steam to liquid on the outside of a pipe with water flowing through it. So the pipe outer diameter is 3 centimeters, the length is 35 meters. The steam condenses at a rate of 130 kilograms per hour. So it's telling you the rate of condensation. Determine the rate of heat transfer per unit area. So we're going to have it over like an area term, or our units are going to be like per square meter, from the steam to the cooling water flowing through the pipe. And then it gives you a little hint. The change in energy of a fluid that condenses from saturated vapor to saturated liquid is referred to as a latent heat of vaporization. This is also discussed in the chapter. So if you did your reading, you should have kind of been introduced to these terms. So to find this energy, you need to use your property tables to find the appropriate change in enthalpy between your saturated vapor and your saturated liquid phase. So your saturated vapor being your steam, your saturated vapor, your liquid being this condensated steam on the pipe. Enthalpy difference is the appropriate choice in this case because it includes fluid's internal energy change along with the work done against pressure due to volume change. So this question gives you a lot of information, and it's trying to make it more clear, but at the same time, it kind of just adds more information and it can sometimes make it a little bit more confusing. But one of the things that it tells you is that we need to figure out here we need to figure out our rate of, oh geez, now I'm not gonna remember what it says. And of course I didn't leave it pulled up. Let me reopen the problem statement, sorry.
It says rate of heat transfer per unit area from the steam to the cooling water flowing through the pipe.
Okay, great. So we are asked for the rate of heat transfer. Golly, I am so over Zoom. I can't wait till we're back in person. All right, so we're asked for the rate of heat transfer per unit area of the pipe. And we're told that this is going to be related to the enthalpy because of the latent heat of condensation. So this is related to enthalpy change, which is the latent heat of condensation. Latent. Are you okay? Thought my dog was about to throw up, but he seems to be fine. You okay? Latent heat of condensation. And so we care about the latent heat of condensation from our enthalpy from our saturated vapor to our saturated liquid. And we actually have a term for this, which is H sub Fg. And we can look this up in the property tables. So we are told that we're interested in finding this enthalpy value per unit area because this is representing the enthalpy change from our saturated vapor to our saturated liquid per unit area. So we know that we're going to probably need to incorporate the area of a pipe. The area of a pipe, so area of a pipe, this is going to be pi dl equals area of a pipe. We're given the diameter and we're given the length, so we can easily calculate the area of a pipe. We are told that this enthalpy change is happening with this pipe. So we have this pipe. We have cooling water that's flowing through it. We have steam that's like condensing on the face of it. And this is occurring at a temperature of 40 degrees Celsius. So we know that we can look up our H sub Fg values from our table where temperature is going to be at 40 degrees Celsius. And we know that this is a saturated liquid vapor table. So we know that this is going to be table A4, I believe. So we want to figure out the rate of this enthalpy change that's occurring per unit area. So as of right now, we know that we have this enthalpy change that's happening. We know per unit area. We know we can look this up in a table. We know that we can calculate this based on the diameter. But we also have this rate of what's happening that's going on. So we're told that this is occurring at a rate, this condensation is occurring at a rate of 130 kilograms per hour, I think. Is that right?
Yeah, that's right.
Okay. So we also have a rate that this condensation is taking place. So we need to include this rate here. So rate of condensation. Times our enthalpy change per unit area. So this is going to give us units kilograms per hour times our enthalpy, which is kilojoules per kilogram because it's specific enthalpy. And then we have area down here, which is going to be meters squared. So if we look at these units, our kilograms are going to cancel. We can convert these hours into seconds, which would give us kilowatts or kilojoules per second, and then kilowatt per meter squared, which would give us what we're looking for, right? So the rate of heat transfer, so the rate of energy change, which should be something like kilowatts. So energy change, the change in energy over time is going to be equal to power, or the change in energy over time, kilojoules per second, and then per a unit area. So the units kind of make sense. We're told in this little hint here that we're going to try to use this rate of condensation times this change in enthalpy that's occurring. This is the latent heat of condensation, and we want it per unit area. So this seems to kind of make sense to us logically when we check the units. Now we can just look up our values that we need. So we are already given this rate in the problem statement. We're able to calculate this right off the bat. So we need to look up our H sub Fg from the table. Based on the solution, it looks like at 40 degrees Celsius in table, I believe it's A4, our H sub Fg is 2,406 kilojoules per kilogram. So we have 130 kilograms per hour and then 2,406 kilojoules per kilogram as our H sub F term, table A4 at 40 degrees Celsius, 2,406 kilograms per kilojoule. This is representing our enthalpy change. This is our rate of condensation that's occurring. And then our area here is pi dl. So pi, our diameter is 3 centimeters. And then the length is 35 meters. So now we need to do some unit conversion. Up here, we want to convert hours. So 1 hour is 3,600 seconds. And down at the bottom, we want to convert centimeters into meters. So 1 meter is 100 centimeters. Wait, that doesn't cancel. Sorry, you got to switch those. It's the right ratio, but I wrote them the wrong way. So 1 meter, which is what I want left, is 100 centimeters. So now my centimeters cancel. I have meters squared. My hours will cancel. My kilograms will cancel. My units left are kilojoules per second per meter squared. So kilojoules per second per area. And then this works out to be about 26.3 kilojoules per second per meter squared. I think that out of this problem, knowing how to incorporate per area is an important concept. So if I ask you what is the rate of heat transfer per unit area, knowing how to incorporate per unit area into there is an important concept. I think understanding that the change in enthalpy from a steam to a liquid is going to be this value, right? This represents the change in enthalpy from a saturated vapor to a saturated liquid, right? So this is H sub G minus H sub F. That's the equation for this. That's an important thing. Knowing how to use table A4, I think, is important. But coming up with this equation yourself takes a little more, sitting down and working through a homework problem, working through your units, trying to figure it out than I would give you on an exam. So I think incorporating a per unit area, totally fair game. Needing to understand that the change in enthalpy is represented by this enthalpy sub Fg for a saturated liquid vapor, fair game. Understanding that when we're saying things like a saturated steam and a saturated liquid vapor, that means you know exactly what table you're using. That's fair game. Checking your units, definitely fair game. But coming up with this equation right here, I think is a little tougher than I'm going to be assessing because the question is a little confusing about what rate you're actually trying to get.
Thank you.
Yeah, you're welcome. Other questions?
For the HFG, you said it's H sub G minus H sub F. Is it ever like the other way around? Like, would we have to convert it like that? Okay.
No, it's never going to be the other way around. So it's very controlled as being that way, because if we look at our different phases, right? So we have this kind of graph here where this is a superheated vapor. This is a compressed liquid. Right here is where we have our saturated liquid. Right here is where we have our saturated vapor. So this is going to be our sub G term. This is going to be our sub F term. F, I just remember for fluid and gas, but whichever one. And so when we're looking at these values, this whole region in here is considered the saturated liquid vapor region. This is all going to be in table A4 and A5. And the values for this saturated vapor are always going to be larger because it's about to come up higher. It's always going to be larger than these. So your enthalpy sub G is always going to be greater than your enthalpy sub F. Most of the time, much greater. So it's in order to get the distance of this line, we always subtract H sub G, H sub F from H sub G to get how big this line is here. And that's why this is representing that change in enthalpy. Oops. Because that difference between them is representing, if you're subtracting your sub G value from your sub H value, you're getting this whole change that's occurring here from as soon as you're a saturated liquid to a saturated vapor. This is also why sometimes we need to include quality, because sometimes you don't want this whole line, you only want part of the line that's occurring, because maybe you're not totally going from a saturated liquid to a saturated vapor, you're going from a saturated liquid to 60%, X equals 60% of a saturated vapor. So now you know that it's not going to be this whole line, it's just going to be this point right here. Yes, so you can use H sub Fg from the chart. The one that's not there is specific volume sub Fg. So that one you have to know how to calculate yourself, which is going to be a specific volume of G minus specific volume of F. But the H sub Fg value is one that's calculated in the table. So your superheated vapor, your saturated liquid vapor, your compressed liquid, I would recommend reviewing the major ones that are deciding each of these. So if you have a saturated vapor and you are heating it up more and your saturated temperature is much higher than your saturated temperature for a saturated vapor, you're a superheated vapor. Kind of those relationships that we did, remember, where, you know, if your Tsat is higher than your Tsat for saturated liquid vapor, if your temperature is higher than your Tsat for saturated liquid vapor, that's when you're superheated vapor. If your pressure is much larger than your saturated pressure for a saturated liquid vapor, then you have a compressed liquid. Some of those comparisons, so you make sure that you know which table you're using. I would also look at keywords that indicate you know what table you're using, such as quality, such as saturated, the term saturated, such as, yeah, those are kind of two of the big ones. Quality, saturated, steam is heated to whatever. If you're heating up steam to an additional point, a lot of times that's kind of indicating you might be a superheated vapor. Those are kind of two big ones.
Saturated could be two different things, though. Unless it's, well, yeah, it could be three things because it could be a vapor, a liquid, or a mix.
Right. So you could have saturated vapor, saturated liquid, or saturated liquid vapor, but these are all going to be in the same tables.
Oh, okay.
Table A4 and A5. So these will denote if you're using, you know, Y sub G, Y being just enthalpy, specific volume, anything, or Y sub F or Y sub FG. But these are all going to be from the exact same table. And a lot of times we use table A4 and A5 for water, and I think it's table A12 and A13 for R134A. We use these as a starting point. So here's where you're going to assume that you're a super saturated liquid vapor if you don't really have any clue, and you're going to check your temperature and your pressure typically to see if you're higher or lower, and you can confirm if you're a superheated vapor or a compressed liquid, or if you actually are a saturated liquid.
I actually have another question. I don't know if you feel kind enough to answer this or not, or if, I don't know if it's a problem or not. But can you tell us if the table is going to come in several sheets and we pick through, or are they going to be homework represented like you did? Or sorry, in class represented, where it's just like, boom, here's this.
So they are like added like appendices. So this is like the example. This is what I'm going to be giving you. So I've kind of copied the page, shrunk it down a little bit, and they're going to be given to you in the back of the exam like an appendix.
Okay.
So it's not going to be like the in-class activities where I pull out just like 5 lines. You're going to be given the whole table. What tells us when to use table A4, A5? Because one table has temp in first row and one has pressure in the first row. Yeah, so most of the time, if you are given, so for the example problem I worked before, we were only given temperature, so it's pretty easy to know that we only need to use temperature. For other problems, sometimes you'll only be given pressure. For some problems, you will be given temperature and pressure, so you need to determine which one to use. The book kind of explains this a little bit, but in general, there are a few basic rules. So if you're given a temperature and you're given a pressure and you're told the pressure stays the same, most of the time we would use pressure. Yeah, I can go over a problem like that where we're given both. Let me try to find one. Let's see. Okay. So for instance, if you're told that you have water at 75 degrees Celsius and 500 kilopascal, and you want to determine the internal energy, this is an example. Okay, so you have water at 75 degrees Celsius and 500 kilopascal. You want to determine the internal energy. So we know that we have temperature at 75 degrees Celsius. We know that our pressure is 500 kilopascal, and we want to determine the internal energy. So in this case, we're given both temperature and pressure, but we don't know what table to use because we're not told anything like this is a steam, this is a saturated liquid, this is whatever. We're just said it's water. So we don't really know. So what we're going to do is we're going to start by going to table A4 and A5 and try to determine if that's the correct table that we can use, or if we need to use this superheated vapor or the compressed liquid table. And for this problem, we're going to, and typically this is, if you're given both temperature and pressure, typically this is what you're going to be doing. You're going to go to your pressure table. So table A5, because you're given pressure and you want to check your saturation temperature. So we're going to go to table A5 at 500 kilopascal. And we can see that our Tsat is close to 151 degrees Celsius. So remember, if our temperature is less than Tsat at a given pressure, then we have a compressed liquid. If our temperature is equal to Tsat at a given pressure, then we have a saturated mixture. So saturated liquid vapor, saturated mixture. And if our temperature is greater than our Tsat at a given P, then we have a superheated vapor. And this is kind of why, in general, you're going to pick the pressure to follow if you're given both temperature and pressure, because we have these comparisons that are helpful. So in our case, we have our temperature at 75 degrees. Our Tsat is at 151. So our temperature is less than Tsat, which means that we have a compressed liquid. 500 kilopascals for this like not super hot water is also kind of a hint. That's a lot of pressure for that water. So that it kind of makes sense that it could be a compressed liquid. And so that means that we're going to either use table A7, or we can just use our Y sub F values and assume that we're going to still use our saturated liquid vapor table, so table A5, but just use the values that include only our saturated liquid. So therefore, we can go to okay, so we can go to our compressed liquid table, which I believe is A7, if I'm not wrong. Okay, so we can go to our compressed liquid table, which is table A7. And we have 500 kilopascals, so this is going to be 0.5 megapascals. But when we look at our compressed liquid table, the lowest pressure available there is 5 megapascal. They have 5 megapascal, 10, 15, 20, 30, and 50. So we can't really use our compressed liquid table for this. So now we're going to go back to our saturated liquid vapor tables, table A4 and A5, and try to figure out what we are going to use. For a compressed liquid, we're going to be using our table A4 to determine what our internal energy is at 75 degrees Celsius. In this case, our pressure was much lower than our compressed liquid table, so we can't use that. We need to go back for our saturated liquid vapor table. We're going to use only the ones that have the subscript of F. And this time we're going to be looking up the compressed liquid at a given temperature. So our internal energy at a given temperature, not at the pressure. So we were using the pressure to kind of do this check here, but we're using this temperature to determine what the internal energy is. So this internal energy at 75 degrees Celsius is going to be our internal energy sub F at 75 degrees Celsius. And this is going to be roughly 314. Yep, 314 kilojoules per kilogram.
So we use temp, but we'd use pressure if the pressure was constant?
If you were only given pressure, well, we're for this problem, we're assuming temperature and water, or temperature and pressure are constant. But typically we're going to use, and for the exam, just as a rule of thumb, I would do this. You're going to use pressure to determine your table and do this little TSAT test. Then you're going to use your temperature to figure out what value you actually have for your internal energy. Does that make sense?
Yes, thank you.
Okay. Other questions? Okay, so Layla, you're asking how do I know to use U sub F and not U sub G? So if you remember, U sub F is for 100% saturated liquid. So this is all going to be liquid. There's going to be no vapor in there. U sub G is going to be for all saturated vapor. It's entirely steam. There's no liquid component. And then my U sub FG is going to be a mixture of saturated liquid and vapor. So for compressed liquid, I know that there's no vapor. It's under too high of pressure. Yeah. And well, water doesn't really tell us anything because water can be ice or steam or superheated vapor or anything. This is just telling us it's not refrigerant. So we're not told anything about this water, but we were able to use our pressure to check to see what phase we're in. We figured out by comparing the saturated temperature that we are below our saturated temperature for this given pressure. That means we're a compressed liquid. So you can use the compressed liquid table, but our compressed liquid table is not big enough for us to use in these textbooks, which means that we need to use the saturated liquid vapor table. But our saturated liquid vapor table contains values for both liquids, vapors, and everything in between. We know that a compressed liquid, we are only a liquid. That's why we're using this saturated liquid value. Okay.
When do we know when to multiply that by like a mass? Because isn't it specific? Isn't it a specific U?
Yes. So this is our value for specific internal energy. And I did actually, this is a lowercase. It's hard to tell with my U's what's uppercase and what's lowercase. If I asked for total internal energy, if this was uppercase, and to avoid confusion on the exam, it's very obvious when it's lowercase and it's typed, but I would also probably write like total internal energy. And that means that you would need to multiply this by some mass term.
Okay, and so would you include the mass in the question, or would we have to go to like the density of water and just start working it out?
So there's no real way you can work it out for this problem because you're not given volume, you're not given any like cross-sectional area, you're not given anything. So I would either need to give you information that you could get mass, so something like quality, something like volume, or I would give it to you. Probably for the exam, I would expect you to know things like the density of water, which you already know, that you can figure out your mass by multiplying density and volume, that you can figure out mass from quality. So if you're given quality information, you know, quality is related to mass. And there are several ways you can find mass. I wouldn't make it, you know, too tricky, but yeah, you would need more information for this problem in order to even find out anything about mass.
Okay, thank you.
Yeah. Other questions?
Can we do some of the questions from chapter 4 that require us to use like the energy equation that we used from like chapters 1 and 2?
Yeah, definitely. I don't think, yeah, okay. So I love these energy equations. I'm gonna work one that we kind of already worked, but I think I did it as an example in class, but I'll just do it again because I think it's pretty good. So this is one that I like a lot. This is the one where you have this rigid tank that's divided in half. On the it's divided in half, so equal parts. One side of the tank contains 5 milligrams of water. And the pressure on this side is 200 kilopascal. And the temperature is 25 degrees Celsius. The other side is evacuated, which means this isn't a vacuum. So this is slightly different than one we worked before, where I'm putting this one now in a vacuum. We remove this partition, so we take this partition out, and this water, so this is water in here. This water can then fill the entire space. The water is allowed to exchange heat with its surroundings until the temperature returns to its initial temperature of 25 degrees Celsius. So since this is an evacuated space and this is in a vacuum, this time we're going to actually have our heat that's coming in, because this side is going to be at a much lower temperature, ostensibly I think 0, since it was kind of developed in a vacuum. So it's not just like open space, it's in a vacuum. So we're gonna remove this partition, the water's gonna come in here, it's gonna cool off. So if this is at 0 and this was 25, or this could even be colder than 0, we're not told what it is. It's gonna be colder, and then it's eventually gonna get heat from the surroundings until it returns to 25. So our initial temperature is 25, and our final temperature is gonna be 25. Bless you. We're asked in this problem to determine the volume of the tank. We're asked to determine final pressure. And we're asked to determine heat transfer. This is example 4.6. Okay, so for number 1, to determine the volume of the tank, or for part A, I guess, to determine the volume of the tank, we're told mass, we know density of the water, so we could maybe figure out volume that way, but we don't know if the density of the water is staying the same because we have this temperature change that's happening, and we aren't going to use that equation. We have other information that gives us more valuable information about volume, and that's going to be our property tables. So we know that our we are going to go to table A4 and A5 because we know that we have water. So at table A4 and A5, we can see here is another example where we have both pressure and temperature. So first we're going to go to table A4 and, or we're going to go to table A5 because that's where we're going to check our pressure at. So our TSAT for 200 kilopascal is going to be 120.21 degrees Celsius. So our temperature, once again, is lower than our TSAT, which means that we have a compressed liquid at our first temperature, our T1, our starting temperature. We don't know our final pressure. That's what we're actually asked to calculate. So we can't really get information about our second condition quite yet. But we know that we are going to be working with a compressed liquid. So now we can figure out our specific volume for a fluid at 25 degrees Celsius. So we use temperature to check what table we're in. We're using temperature to look up our values. Yeah, he's snoring away, I know. And so we have our specific volume at 25 degrees Celsius from table A4. And this is going to be 0.001003 cubic meter per kilogram. And remember, we're using only our saturated liquid value because this is a compressed liquid. This 0.2 or 0.2 megapascal is too low to use our compressed liquid table. So we have to use our saturated liquid vapor table to get our saturated liquid value here. So now we have our specific volume for our starting condition. So this is like at 0.1. And we know that our total volume is going to be mass times our specific volume. So our total volume at 0.1 is going to be our mass times our specific volume at 0.1. Our mass of this closed system is not going to change. Our mass is always going to be the same here, 5 kilograms, 0.001003 cubic meter per kilogram. So our volume of this side, our volume 1, is going to be 0.005 cubic meter. And we know that this tank is divided equally in half. So our volume of our tank is going to be equal to 2 times our volume of our 1/2. So 2 times 0.005 cubic meter, which is going to be 0.01 cubic meter is the volume of the tank. So this is our answer for part A. The volume of our tank is 0.01 cubic meters. We can also figure out our specific volume at 0.2 because this is just going to be the volume of the tank divided by the mass, because the volume of the tank overall is how much our system is filling at 0.2. So the volume of the tank divided by our mass would be 0.01 cubic meter divided by 5 kilograms is equal to 0.002 cubic meter per kilogram. We don't need to box that because we're not asked for that. We just need that later. Which this should make sense because this is double our specific volume at 0.1. So for the same mass, the ratios should still apply. So our volume of our tank at 0.2 divided by the volume of our tank at 0.1 should be the same ratio of our specific volume of our tank at 0.2 over the specific volume of our tank at 0.1 when mass is constant. So when you have a closed system, which in this case we do. So you can either work the problem this way, or you could just set up this ratio here. We know all three of these values. So we have 4 values, 1 unknown. That is fine. All right. So we know that I'm going to clear some of this. Okay. So we know the volume of the tank here is going to be equal to 0.01 cubic meters. That's our value for A. For B, we want to determine final pressure. So we want to determine the pressure at point 2, or the pressure in this entire tank. So we now know the specific volume of the entire tank. We also know the temperature at point 2. So we know for part B, we know T2 is equal to 25 degrees Celsius. And we know that our specific volume at point 2 is going to be equal to 0.002 cubic meter per kilogram. Do we know if this is our specific volume sub F, our specific volume sub G, or our specific volume sub FG? Do we know that?
Is it F because it's still compressed?
We don't know it's still compressed though, right? Like it was compressed when we had this partition, but then we gave it a bunch of extra space.
Did you look at the initial tables to see what what that would be, its specific volume would be under the conditions in A4 or A5?
Right, exactly. So you guys are both on the right tracks, right? We would need to check if it's still compressed, because if it's still compressed, then we're going to use this value. If it's not still compressed, then we're going to be able to use, if it's not still compressed, that gives us information that now that it's some sort of mixture, and that would give us information about pressure. So we're going to take the value of our specific volume at point 2 and see how it relates to our table A4, which is where we're given our temperature at 25 degrees Celsius. Sorry, I might sneeze. Okay, so when we go to table A4 at 25 degrees, we can see that our specific volume for our saturated liquid at 25 degrees, we already know is 0.001003. Our saturated liquid, our specific volume for our saturated vapor, too many terms, is 43.340. These are both going to be cubic meter per kilogram. Cubic meter per kilogram. And now we can check to see if where our saturated, or where our specific volume for our entire tank falls. And we are slightly higher than our saturated liquid specific volume. So we're at 0.002. So we're about double this, which means that we are now in saturated liquid vapor territory. We are in mixture territory. We have a little bit of vapor. We are no longer a compressed liquid. So the fact that we're higher than what this compressed or saturated liquid would be tells us that we are now somewhere in this plateau region. So we're now somewhere in between here, instead of being down here, or instead of being up here, because we're not higher than this specific volume here, and we're not lower or equal to this specific volume here. That means we're in this saturated liquid vapor region, which means we can still use table A4 and A5. And if we now look at our, so our pressure at point 2 is going to be equal to our saturation pressure. So our Psat for this given area in here at 25 degrees Celsius, which is going to be in table A4 as 3.1698 kilopascal from table A4. Keep in mind, I'm using the 8th edition of the book because the 9th edition of the book is like in a 3-ring binder and it's easier for me to use the 8th edition. Sometimes these are slightly different values in the 9th edition, but they should be very, very close. Sometimes it's like 3.1684 or something, but they're very close. Okay, so now we know that since we are in this saturated liquid vapor region, we have a Tsat and a Psat for this whole region. Since we know our temperature already, we're going to be at this Psat for this whole range. That's why we can just look it up in table A4 once we know that we are in this table by confirming our specific volumes, and then we know our temperature that we're looking it up at. So there we go. B is answered. Our P value is going to be 3.1698 kilopascal. And now we just want to know about heat transfer, which Emma, I'm finally getting to what you were asking about. So for part C, we want to know heat transfer. Heat transfer is going to be our trusty Q value that we've been working with. We know that since this was a vacuum space, this was colder. We have our 25 degree expanding out. It's going to drop down to maybe something like 10 degrees, slowly absorb heat from the surroundings, come back up to 25 degrees. So we know this heat is coming in. And we're asked to find how much of this heat is transferring in. So remember that energy can cross a closed boundary system. For this exam, all you're looking at is closed boundary system. Then your energy can transfer the boundaries through heat and work. In chapter 5, we start to look at open boundaries, so control volumes. But for this exam, these are all closed systems. Heat and work are the only way that you can have energy transfer across a closed system boundary. B, so Noah's question, so for B could have just been answered with only the given temperature, right? Yes, it could have been, but you have to make sure that you're checking what table you're using. So first you need to check that you are able to use table A4 and A5, and the only values that you had for that were temperature and then specific volume at point 2. So you need to first do a check and then you can answer it with just the given temperature. If you're just looking with the given temperature, you don't know if you're using compressed liquid, saturated liquid vapor, or superheated vapor. So the first thing to do is always check that you're using the right table. All right, so for C, we want to figure out heat transfer Q. The way that we have heat and work interacting with our closed boundary here is through our energy equation, which is going to be the change in energy of our system is equal to energy in minus energy out. This becomes our change in kinetic energy plus our change in potential energy plus our change in internal energy is equal to our energy coming in, which is Q in, and then minus work out. This partition is removed by us. It's not a piston. There's no boundary work that's occurring. We're not heating this up using electrical heater or anything. It's passive heating from the air. We don't have any spring that's acting here. We don't have any sort of additional work. So we know that there's no work that's occurring. This is also a closed stationary system, so there's no kinetic or no potential energy. So our equation just becomes our change in internal energy is equal to our heat transfer coming in. Okay, so we want to solve for this heat transfer coming in. So we're going to need to manipulate this internal energy here. We know that we've been working with an equation for specific internal energy, which is our so first I'm going to convert this into our mass times our specific energy at 0.2 minus our specific energy at 0.1 is going to be equal to Q coming in. We know that we've been working with our equations for internal energy, which it could become our C sub P times delta T. Or we could possibly use our property tables. So for this question, we need to determine if it makes more sense for us to use our property tables or for us to use our C sub P times delta T. And one of the main giveaways for this is that we don't have a delta T. And we've already been working with our property tables here. So it seems like we're going to need to choose our property table here. If we were working with a temperature change, and that's kind of part of the driving force here, if we were working with a temperature change, we might want to use this MC delta T equation. But since we aren't having a temperature change, and since we are already using the property tables, it seems like we can just use the property tables that we already know. We already know from part B that we're able to use tables A4 and A5 because we're a saturated liquid vapor at this point. So we can use the saturated liquid vapor table. So it would be easier to just look up these Q values than try to look up a CP and then still have this cancel to 0, which wouldn't work, doesn't give us any value anyway. So we would need to maybe change this into enthalpy, where if you remember our enthalpy equation, enthalpy is equal to, I hate that it keeps doing that. Enthalpy is equal to internal energy plus pressure times volume. But we would still need to look up our internal energy as well as incorporate our pressure and our volume for each of these points. So it doesn't really seem to be that we should use either this MC delta T or change it to enthalpy. It seems like it would just be easier to look it up in the property table. So that's what we should do. So we have our U2, which is going to be our saturated liquid vapor value. And we have our U sub 1, which we already know is going to be for our compressed liquid. So at 25 degrees for our property table for a compressed liquid, this is going to be 104.83 kilojoules per kilogram. Now we have to figure out how to get our internal energy at 0.2, which is going to be more of a mixture. So in order for us to be able to get this value, we're going to need to use the equation of U sub F plus X times U sub FG. But we don't know our X value here. We can look up U sub F from the table, which we just did. We can look up U sub FG from the table, which we can easily do on the same table. But we need to figure out this X value that's occurring here. So we can figure out X, our quality, from a few ways. We can figure out quality as the mass of the gas over mass total, but we don't have information about mass of the gas. We only have information about mass total. We can figure out X by doing the generic formula where we have our Y value minus Y sub F over, Y sub F over Y sub FG. So for instance, this could be enthalpy. This could be our internal energy, or this could be specific volume. So Y just being a generic space filler here. The information that we have for this problem already from part 1 is specific volume. So I'm going to use specific volume. So specific volume of my total tank will give me my X at my 0.2 minus specific volume of my liquid, saturated liquid, over specific volume of my saturated liquid vapor. But remember, you can't look this value up from a table. It has to be from the subtraction of your specific volume of your gas minus specific volume of your vapor. So that should say F.
It's really hard to see on the, there we go. Thank you.
Okay. You can see it now? Okay. Let me try to make that writing a little more clear. Specific volume of my liquid. So we know my specific volume at 0.2 because that's what it was asking for in question part A. So this is 0.0. So this is my total volume. If you remember, my specific volume was 0.002. Yeah. So 0.002 cubic meter per kilogram as my specific volume. My specific volume of my saturated liquid was 0.001003 cubic meter per kilogram. Then the saturated, the specific volume of my saturated vapor was 43.34 cubic meter per kilogram. And the saturated liquid specific volume is this same 0.001003 cubic meter per kilogram. Hold on, I have to plug in my computer. Okay. So when we work all this out, we get our quality value to be very, very small. So we're going to have a very small value, about 0.01 divided by 43. So this gives us 2.3 times 10 to the negative 5, or 0.000023. So our quality is very small. We kind of already know this because we are so close to the specific volume for a saturated liquid, and we are not anywhere close to the specific volume for a saturated gas, which means that we have a very, very, very small amount of vapor. We went from a compressed liquid to a almost compressed liquid that has just a little bit of vapor in it. So it makes sense that our quality is very small because the mass of our gas is going to be very, very small. It's going to be mostly all liquid. So now we have our X value, and we have everything else that we need to solve. So we have our U sub F as 104.83 from the table, but it's also right here. And then we have our quality, which is 2.3 times 10 to the negative 5. And then our U sub FG, which we can also look up in the table. It's that middle term there, which is 2,304.3 kilojoules per kilogram. And when we multiply all this out, sorry, I'm getting crushed for space, it is 104.88 kilojoules per kilogram as our U2 value. So we know our Qn is equal to mass times U2 minus U1. We know mass to be 5 kilograms. We know U2 to be 104.88 0.88 kilojoules per kilogram. We know U1 to be 104.83 kilojoules per kilogram. So this is going to be 0.05 kilojoules per kilogram. So our value here, 0.05 times 5 is 0.25 kilojoules, since the kilograms will cancel. So this equals 0.25 kilojoules. This is our heat transfer coming in plus 0.25 kilojoules that are coming in. This is actually similar to the problem that I had chosen to do. Since we only have a couple more minutes in class, I'll just kind of go over that problem very quickly. So for the problem that I was going to go over as a review, 1 cubic meter of saturated liquid water at 200 degrees Celsius is expanded isothermally in a closed system until the quality is 80%. X is 80%. Determine total work. So the last question was total heat transfer. This says determine total work. Why is it doing that? Determine total work produced by expansion. So for this problem, we're given temperature. We're not given any information about pressure. So we're going to use temperature to determine which table we're in. So when we look at our table, oh, we don't actually have to do that. Sorry, I was trying to figure out in my notes how I just knew what table to use. We're told that we have a saturated liquid, 1 cubic meter of saturated liquid water, which tells us right off the bat that we can use table A4 and A5. So when we look at table A4 at 200 degrees Celsius, our P sat, which is going to be equal to our pressure at 0.1 and our pressure at 0.2 because this is an isotherm. Our P sat is going to be 155 kilopascal. I think it's like 154.9 or something, but just 155 for this question. We also know that our specific volume at 0.1 is going to be the specific volume of our saturated liquid in table A4 or A5, which is 0.001157 cubic meter per kilogram. We're asked to determine total work produced by the expansion. So we know that we have a closed system that's expanding. It's expanding in something like a piston. So we know that our work equation, work is going to be boundary work, which is equal to the integration between 0.1 and 0.2 of pressure times our change in volume. This is an isotherm, so this becomes very easy. Yes, so isotherm means that it's constant temperature, but we okay, sorry. I'm trying to go fast, which means I'm skipping stuff that I was originally explaining, but now we're getting close to going over time. So this is an isotherm, which means we have a constant temperature. So the whole time we're going to be at 200 degrees Celsius. We are told that we have saturated liquid water at our start, which means that we're starting at only our Y sub F term. Then we are expanding until we're reaching a quality of 80 degrees Celsius. I'm sorry, a quality of 80%. So this means that we are expanding from a saturated liquid to a saturated liquid vapor where the quality is at 80%. we are staying in our saturated liquid vapor range for the entire time. We are in this plot, we are still in this plateau. So we are going from a saturated liquid to 80% of a saturated liquid vapor. We are staying in this region the entire time, and we are staying at 200 degrees Celsius. So our temperature at 0.1 is going to be equal to our temperature at 0.2, which means we are at 200 degrees Celsius. But since we are staying as a saturated liquid vapor, our pressure at 0.1 is going to be equal to our pressure at 0.2, which means we are going to be at our saturation pressure for this whole region. So since we know that this is an isotherm and we are expanding from a saturated liquid to a saturated liquid vapor, we know that the pressure and the temperature are going to be at the same. So our temperature is 200 degrees Celsius and our pressure is 155 kilopascal for this entire question. So while isotherm is only telling me about temperature, this X value here, quality is indicating that we are still at a saturated liquid vapor, which means that we are at our saturation pressure for this whole region. So our temperature is constant, our pressure is constant, which makes this working out easy. Pressure is going to be equal to volume 2 minus volume 1. We already have information for our specific volume at 0.1, which is helpful. We have information about X, which gives us information about mass. Our specific volume at 0.2 is going to be equal to our specific volume at our saturated liquid plus our quality times our specific volume of our saturated liquid vapor, or specific volume of our gas minus specific volume of our vapor. I'm sorry, specific volume of our vapor minus specific volume of our liquid. So we know that V sub F is 0.001157. We know that quality is 80%. And then from the table in the back of the book, we know that V sub G is 0.1. So we know this is 0.001157. We know that X is 80%. We know that from the back of the book, V sub G is 0.12712. And we know that V sub F is still 0.01157. This is all cubic meter per kilogram. So when we work this out, this is 0.12 cubic meter per kilogram as our specific volume at 0.2. So now we know our specific volume at 0.1, we know our specific volume at 0.2, and we know our pressure. We want to figure out our total volume at 0.1 and 0.2, and we have information about quality. So we could potentially figure out information for mass from that. But the thing is, we're not given any other information about mass. We're only given information about our total volume at 0.1. So we know our ratios, our specific volume at 0.2 over our specific volume at 0.1 is going to be equal to our volume at 0.2 over our volume at 0.1. We have our specific volume at 0.1, we have our specific volume at 0.2, we have our total volume at 0.1 given in the problem statement. And therefore we can solve for our volume at 0.2, which would give us everything that we need to solve for our boundary work equation. So I'm gonna erase some of this to give me some more room. I'm almost done, I promise. If anybody has to go, that's okay, this is recorded. I know we're still within the class time, but I always try and end by 12:45. But okay, so we have specific volume at 0.2 over specific volume at 0.1 is equal to volume of 2 over volume of 1. Solving for volume of 2, this is going to be volume at 0.1 times this ratio, specific volume of 0.2 over specific volume of 0.1. So this is 1 cubic meter times by 0.102 cubic meter per kilogram over 0.001157 cubic meter per kilogram. So these units will cancel out and you'll be just left with cubic meter, which is 88.16 cubic meters. So now we have everything to solve this boundary work equation. We know our temperature at 0.1 and 0.2 is going to be our saturation temperature because this is a saturated liquid vapor. So 155 kilopascal times our volume at 2, which is 88.16 cubic meter, our volume at 1, which is 1 cubic meter. So it has expanded a lot. It's expanded from 1 cubic meter to 88 cubic meters. So it expanded a lot. We got a lot of work done. This work works out to 1,3,3,5,5,2.8 kilojoules. So 155 times 87 is about 1,333,522 kilojoules. Or I would prefer if you wrote it as 1.335 times 10 to the 5 kilojoules is our work done. Oh, did I copy that wrong? No, I rounded to 1,155. So it's 1,154.9 kilojoules per kilopascal, or kilopascal, sorry. So this should be 1,555. I copied that from my notes wrong. It is 1,555 kilopascal.
I have a question.
Yes.
I'm terribly sorry, but I got distracted when you told us how you knew that pressure was constant. Can you repeat?
Yes. Okay. So we have our diagram, right, where we have our compressed liquid, our superheated vapor, and then we have our saturated liquid, our saturated vapor, and this whole region is our saturated liquid vapor mixture. So for this question, we are expanding from a saturated vapor, I'm sorry, a saturated liquid, so all liquid, to 80% saturated vapor. So we're moving a lot more towards saturated vapor. But I know that in this whole region here, I'm going to be at my saturated pressure for my given temperature.
Okay, so that just gives us that as the constant then.
Right. So I'm told I have an isotherm, which means I know my temperature is constant, but then I'm told I'm moving from a saturated liquid to a saturated liquid vapor, which means that this whole region here is going to be in my PSAT region, my saturated pressure region.
Okay. Sorry about that. Thank you.
No, you're fine. So the problem that I worked was problem, sorry. If you want to review it on your own on Slater or Chegg or whatever, the problem that I just worked before was problem 4-9 on your problem set in the back of your textbooks. Okay, so I know now we're definitely over time. So I hope that was helpful. The homework questions, in-class activities will also be helpful. Knowing how to use the property tables is important. Knowing how to use boundary work equations is important. Knowing the MC delta T, kind of how to use those as well is important.
And then really quick, did you have like a list of problems that you were gonna go over today, but like didn't get to? Like, do you have any that you would recommend?
No, so I've done most of the problems that I like. I do them in classes throughout, or I put them on the in-class activities. So a lot of the example problems in the book that I like, or the problems in the back that I like, I pull them and I put them as in-class problems that I work or in-class activities that we do on Friday. So the only review problem I was going to do is 4-9 in the back of your textbook. And then the rest I was just going to take questions from you.
Okay, thank you.
Yeah. Other questions? Okay. Well, I actually have a meeting at 1, so I need to go. I'm sure all of you need to go as well. But have a good rest of your day. I'll see you Friday in person in Holmes 147 downstairs. Make sure to wear at least one mask that covers your whole mouth, and bring a jacket. It's kind of cold. Bring your calculator, pencil, maybe a drink or a snack if you want to do that. And I will see you on Friday.
Thank you.
Oh, and wear something egg related if you have it. Yes, Josh, good reminder. Yeah, my nose is bleeding.